So my talk will be in some sense a continuation of the previous one by Derishev. And I'll basically discuss the physics of systems called radiation-mediated shocks. These things are not really new. They've been studied in the 70s and 80s of the last century, but only in the context of supernovae shock breakouts, and only in the non-relativistic regime. In the recent years, the interest in these systems has been renewed as it was realized that they are pretty much relevant to many other compact relativistic sources. And as I'll show, the extension to a relativistic regime is non-trivial at all. These things have been, here you have some papers where some of the physics of these things is discussed in various contexts. In this talk, I'm going to focus on gamma ray bursts, but these are much relevant also to shock breakouts in supernovae and in maybe low luminosity GRBs, etc. Maybe Woody Nakar will say something about it in this talk, I don't know. You will? Okay, good. Okay, good. So, okay. So my main focus will be, as I said, on GRBs. So why actually considering those? So there is a motivation, essentially twofold motivation. One is observational in some sense, and the other one is theoretical. There was a very nice overview by Evgeny in the previous talk, so I'm not going to repeat it, but basically we don't know anything about most of these systems. We don't have any idea what is the composition of these jets, if they are magnetic, how the magnetic energy dissipates, etc. I'm going to assume a hydrodynamic system, namely some sort of hydrodynamic outflow that dissipates energy, say, near or below the photosphere, also maybe also above the photosphere. I'll just say that even if your jet starts magnetically, if it's a Poynting flux dominated outflow, if it dissipates its energy well below the photosphere, then in the remaining, it just converts into the hydrodynamic flow, so it's basically similar, as long as your dissipation is in this regime. What I'm going to say may be relevant also there. Okay, so as I said, there is a motivation, and on the observational side, there has been claims that there is evidence for so-called photospheric emission. So here you see one extreme example. This spectrum doesn't look like a typical band or whatever you call it spectrum. It can be fitted by a thermal spectrum. And I think the interpretation here is that there is a thermal component produced in the photosphere, and then something else that you might or you do need to account for the for this component here, underlying component here. However, these things are quite rare. There are very few of those with such a prominent signature of photospheric emission. There are also things that look like this, like two peaks. And here, I think the interpretation by observers is that this lower energy peak is presumably a contribution by a photospheric component, and the rest is something else, whatever. I'm actually going to suggest, to show you, that you can produce this entire spectrum by multiple shocks below the photosphere. Okay, so if you buy these claims that there is a photospheric emission, then obviously you might like to consider the dissipation mechanism and what produces this emission. Going back to the previous discussion, what I think Tzvi said, that there may be several components. I think its conclusion is inescapable. There's definitely several components in these systems. Okay. From the theoretical point of view, the motivation is that we, or at least I, do expect substantial dissipation below the photosphere. This is somewhat model dependent, but still, if you just do the naive estimates. For example, here you see something called collapsor simulation. Essentially, this is a simulation by Lazard et al., where you see jet breakout from a stellar envelope. Here, time goes in this direction. And this is the stellar envelope. And this is a particular progenitor. I don't remember. I think it's a Wolf-Rayet with a mass of 16 solar mass, something like that. What you see here is that the jet breaks out, but it's still being confined by some matter, by cocoons that corks out together with the jet, even at much larger radii than the radius of the envelope, up to here. And if you look at the results here, then the claim is that there is a reconfirmation shock that is produced by the confinement of the jet, which bounces back just below the photosphere at a radius of about 10 to the 12th centimeter or so. So that's what you see here. Yeah, I mean, up to here, the dynamic of the jet is quite similar to the standard model. But then you have this event here where it dissipates a significant fraction. And I think they claim that in this particular simulation, it's something up to something like 40% of the energy is dissipated just below the photosphere at an optical depth of, I don't know, a few, between 1 to 10. OK, so at least in this example, there is I mean, it's suggestive that a significant fraction is dissipated below the photosphere by some shocks.
Sorry, what is eta?
Yeah, eta is this. It's essentially the asymptotic Lorentz factor in the adiabatic fireball model. It's this so-called entropy parameter, or it's an enthalpy parameter. It's notably important here. But I mean, what you see here is this. This event is essentially a shock that. OK, as I said, quick remark. We have no clue how to dissipate magnetic energy, but there are some ideas. And it's possible, again, that the jet starts magnetically dominated. And then above the collimation zone, it becomes unstable. And then magnetic field dissipates, and it continues as a hydrodynamic flow. So with Mitch Begelman, we worked out a detailed model of this. And I should say that it's quite speculative. But if you actually believe that the instability growth rate is sufficiently high, then you get something like this. Anyway, so the point here is that in the context of my talk is that if you dissipate energy in this region, it's essentially like a hydrodynamic flow. You don't care about how the jet started. Of course, it could be that you dissipate the energy by reconnection below the photosphere. This is a whole different ballgame. It's going to be very difficult to account for the low energy peaks observed if you do this. You don't have enough entropy when you dissipate magnetic energy just below the photosphere. But that's a different issue. OK, going back to this. So as I just showed you the reconfirmation shock, but it's also quite conceivable that there are also internal shocks just by fluctuations of the central engine. And here you see, again, a simulation. It's a different simulation by the same group. But now they also superposed rapid fluctuation of the central engine, which are these things that you see here. So you still see this overall event of, let's say, a few seconds, 1 to 2 seconds, which is the signature of this reconfirmation shock. But you see these very spiky peaks, which are essentially internal shocks. And they don't go away. They remain there. And so it could be that you also see, when you see the emission, you actually see an emission integrated over several of these internal shocks, like multiple shock emission. So I'll discuss this possibility. Also, and you see that many of them occur just below the photosphere. Some may occur also above the photosphere and become collisionless. I just want to say something that by internal shocks, I mean, usually people mean collisionless shocks. This is two different things. When I say internal shocks, I mean shocks produced in the relativistic outflow. OK, so they don't have to be collisionless. They are not. So we have to be careful about the terminology here. OK, now, you may ask a question, what is the optical depth at which you expect a shock to form? So if you go to a very naive model of this shell collision, and Omer Bromberg, which is not here, actually did this, then you can calculate the optical depths at shock formation versus the bulk Lorentz factor of, let's say, the slow shell. So the picture here is that you have two shells ejected, a slow one and a faster one, which catches up. They collide somewhere. And this optical depth at radius of collision is what you see here. And gamma is, let's say, the bulk Lorentz factor of the slow shell, for sake of argument. So what you see here is that if the bulk Lorentz factor is not crazily high, and I think that now there are some recent works by Beloborodov and I think by Tzvi also, right, suggesting that the Lorentz factor may be smaller than previously thought. It's not like going to be like 1,000, maybe more like 100, 200. But anyway, you see that if it occurs in this region, it's going to be subphotospheric. And as I claim, these shocks that are produced in this region are not collisionless. They are mediated by radiation. If they are produced in this region, they are going to be collisionless, roughly speaking. By the way, these curves, I mean, each of these curves correspond to a duty cycle. Namely, this one, for example, correspond to a time separation between two consecutive shells, which is the dynamical time. And this one is the longest time scale measured in this particular burst. So the optical depth of shock formation depends also on the time interval between shell ejection in this model. But generally speaking, the expectation is that for moderate Lorentz factor outflows, a significant fraction of this shock will be produced just below the photosphere at an optical depth between 1 to 100 or so. Okay. And then the question, if a shock is formed in this region, what is the structure of this shock and what is the emission of this shock? So let me explain very simply what is a radiation-mediated shock. First of all, any shock has some dissipation mechanism. You need to convert bulk energy to random energy, or if you wish, you need to produce entropy. In these shocks, the dissipation mechanism involves emission and scattering of radiation, of photons. And the basic idea is that radiation somehow, in some way which I'll explain, is produced inside this shock transition layer, or also just immediately downstream. Some of the photons produced in this region stream back toward the upstream region, and they collide with the bulk flow incoming into the shock. They decelerate this bulk flow. So this deceleration is due to essentially inverse Compton scattering on the bulk flow. So while doing so, these photons gain energy. So in fact, the energy of the scattered photons in the shock frame can reach the Klein, or actually reaches the Klein-Shiner regime, which if you transform to the observer frame, it can be as high as 200, 300, maybe even 400 MeV. So you can get very high energies, not GeV energies, but up to a few hundred MeV in the observer frame from these scattered photons. Okay, so this is the basic mechanism. And one question you may ask, under which conditions these shocks should form? So you can very simply calculate this condition. First of all, in order to be radiation mediated, the energy density downstream should be dominant. So this condition should be satisfied, where this is the density of downstream, let's say, baryons, or whatever. And then if you use the jump conditions, then you get this relation. Namely, the shock velocity, and this velocity is the velocity of the, let's say, upstream fluid measured in the shock frame. Okay? It's not the bulk velocity. So this velocity has to exceed this value, and it depends weakly on the density of the upstream matter, or if you want, the density of the unshocked material. And here it's normalized to values typically found in GRBs and in stellar envelopes, etc. So you see that the shock will become radiation mediated already when it's highly non-relativistic. So every relativistic shock must be radiation mediated if it produces in a region, in an opaque region. Also, as I said, the photon must be trapped inside the shock. So this gives you a condition on the optical depth of the shock transition layer. And you can, again, estimate it naively by equating the diffusion time of photons with the shock crossing time. So you find that the optical depth of the shock transition is 1 over the shock velocity measured in units of C. So now this optical depth is optical depth measured with respect to the upstream density. As I'll show you, when you go to relativistic shocks, there is a copies per production. So the number of pairs inside the shock largely exceeds the number of baryons. And the optical depth is much larger. But when you measure the optical depth in terms of the baryon density upstream, this has to be its width. In other words, if you want to produce a radiation-mediated shock, you need that your unshock medium will have at least this optical depth. So as you see, for non-relativistic shock, it has to be like something of a few hundreds, a few thousands. But for relativistic shocks, it's on the order of unity. OK. And this is in the shock frame. OK, a few words about relativistic versus non-relativistic. As I said, the non-relativistic shocks have been studied already in the 70s. You see some key papers here. And all of these works, when computing the structure emission, assume the diffusion approximation. Now, the reason why you can use a diffusion approximation in the non-relativistic case is twofold. First of all, the energy gain is small. In every collision, the photon gain an energy which is much smaller than typical energy. Secondly, the distribution function is nearly isotropic. So it's this fact that the diffusion approximation holds simplifies the problem dramatically. When you go to the relativistic regime, things are vastly different. First, the distribution is highly anisotropic. Actually, in the relativistic case, it's almost beam. Energy gain is large. Then there is another feature, which is the optical depth depends on angles quite sensitively. And as I said, you also get copies per production, which you have to take into account. So this problem is far more involved than the one studied in the 70s and 80s. So it requires some new method and technique to calculate the structures. OK. Now, I said that you need to produce photon in the shock. So where are these photons coming from? There are essentially two sources. One source is photon production by free emission and perhaps also double Compton emission inside the shock transition and just downstream. This is mainly relevant to cold upstream cases, let's say shock breakout in supernovae and these things, where the upstream is cold. The other potential source is just advection of photons by the upstream itself. And this case corresponds to GRBs, as I'll show. So basically, if you advect enough photons, they dominate the photons that are produced inside, and you can forget about those. And there are some important differences between these two cases. For example, here, the characteristic temperature will be much lower downstream than in this case, etc. OK. So just some examples. Here is a velocity profile of such a shock, of a advection-dominated shock. Well, it's you can see the dependence on the upstream conditions. And here is a similar profile for a cold upstream case. And there is very nice analytic solution by Nakar and Sari. These shocks were computed numerically by a group at Weizmann Institute. They also computed the spectrum, as I'll show immediately. OK, OK, now an important point. There are vast differences between the collisional shocks considered by all of you and these radiation-mediated shocks. First of all, in collisional shocks, the dissipation mechanism involves plasma turbulence. So the scale is roughly the kinetic scale, let's say skin depth. So if you plug in numbers, it's typically in the order of 1 centimeter or so. So shock width is very narrow. Because of this fact, these shocks can, at least in principle, can accelerate particles. Okay, because the shock transition layer, I mean, the width of the shock transition layer is smaller than the jar radius of protons, you can accelerate particles. It turns out that it's not that simple, but that's another issue. In radiation-mediated shocks, the scale is typically the Thomson length. So if you plug in some numbers, you get something like 10 to the 9 centimeters. It's much, much larger than any kinetic scale involved. So the first conclusion, these shocks cannot accelerate particles. No way. Everyone that tells you that you have an internal shock forming below the photosphere and accelerates particles and produces neutrinos, so this is a wrong conclusion. The distribution of the particles is roughly thermal in these shocks. A nice thing about these shocks, even though their calculation is quite involved, is that the microphysics is fully understood. Unlike collisional shocks, where people are now doing simulations, but we don't understand much about these plasma turbulence processes. Here, the microphysics is fully accounted for. And so it's just a computational problem. And I believe it will be solved. I mean, it will be done within the next few years, a full calculation of these structures. OK. OK, let me say a bit more about the digital structure, because this is relevant to the emission. Actually, if you look more carefully at what's going on here, is that the downstream region has a structure in the sense that the temperature is not fixed, but it varies. The point is that just downstream, in what termed immediate downstream, the number of photons which are produced in the shock or advected by the upstream is much, much smaller than the blackbody limit. That's why what you get here typically is something called Wien spectrum, but I don't like it. It's really a Planck spectrum with a non-zero chemical potential. Sorry? No, it's OK. We can argue about the terminology and history, but that's not what Wien exactly meant.
No,
that's an extrapolation of Wien. But let's keep the terminology short, and it's Wien spectrum. OK. So the temperature is quite high, and you can actually calculate it just from the jump conditions. Then, as the radiation is advected downstream, you have this photon production mechanism kicks in, like free emission and double Compton, and more photons are being produced until you reach the blackbody limit. So the temperature will vary from some value, which depends on the number of photons produced, up to the blackbody limit far enough downstream. And when you see the emission following breakout, you will first see the spectrum produced inside the shock, but then you will see superposition of spectra produced in the downstream. And this temperature profile is going to be very important for the actual shape of the spectrum that is produced in these things. OK. So one thing you would like to do is to actually try and compute this temperature profile. What is the scale of this thermalization layer? So I call this region here a thermalization layer. So you can actually make a very simple estimates. You expect it to be on the order of 10,000 to 100,000 or more, depending on parameters, and free and double Compton. And they are definitely much larger than the shock widths. So thermalization occurs very far downstream. Here you see results of detailed calculations of radiative transfer. And what actually is computed here is the temperature profile starting at just behind the shock, as you see here. And this is normalized. So this value here is 1. This is T over Ts, which is the temperature computed from jump conditions. And you can see that, depending on the Lorentz factor of the shock, of the upstream in the shock frame, it's typically, as I said, 10 to 100,000. One word about the spectrum inside the shock. As I said, you expect extension of the spectrum above the peak by bulk Comptonization. So when people say inverse Compton, you have to be careful about what they mean. This bulk Comptonization is purely by thermal electrons, but that moving with the bulk flow. It's not scattering by non-thermal particles or anything like that. And basically, as I said, this in the observer frame in GRBs, this can actually reach energies of a few hundred MeV. Here you see an example of such a calculation. Now, this calculation was done for parameters that relevant to breakout in supernovae, not for GRBs, because here the upstream is cold. But what you see is that there is this peak and this broad extension, which is roughly a parallel up to very high energies. And the point that I want to make here is that in this shock, where the upstream is cold and the number of photons is very small, these shocks are actually regulated by pair production. So the temperature of this 200 keV is essentially regulated by pair production. When you go to GRBs, where advection is more important, this peak will be actually shifted to much lower energies, and it will be correspondingly lower. But you will still have this high energy extension, the high energy tail. And we actually verified this with Monte Carlo simulations. And so the general structure you expect is inside the shock is some peak and this hot component. So the main question is, what is the relative energy contained inside the shock to the energy dissipated?
The extension here is up to gamma squared.
Yeah, OK. I don't want to go into it. Yeah, it's because of photon breeding.
Yeah, but in the, just short, in the case that it's advection dominated.
Yeah, then we found some breeding, but I don't have firm results, so I don't want to actually go into it. It's not terribly important for the overall picture. OK, so let me just explain. Let me now go to the last part of my talk and show the results. So let me explain how we calculate. First of all, another difference between GRBs and stellar envelopes is that the shock in GRBs is propagating in a relativistically expanding flow. So the density declines roughly as r to the minus 2, let's say, if you assume a conical flow. And all of these layers have a width which scale roughly with 1 over the Lorentz factor squared, where here gamma is the bulk Lorentz factor. Now, what's happening here, the idea here is that a shock is formed at some radius with some optical depths, and then it just propagates all the way to the outwards. While propagating, it accumulates more and more shock material behind it. So the downstream region grows, essentially. As the shock propagates, more and more material is accumulated, downstream region grows. And as I said, there is going to be some temperature profile. And in this case, because this is a conical flow, there is also adiabatic cooling. So you have also to take into account a change in temperature of every shocked shell here just by adiabatic cooling. So your transfer problem should include this. Now, as the shock reaches the photosphere, where optical depth is roughly unity, it breaks out and emits. First of all, you'll see the emission from the shocked layer. And then you'll start seeing emission from downstream region, from shells, downstream shells reaching the photosphere. Now, what I want to calculate, what I calculated is the integrated spectrum, namely the spectrum of this entire event. OK? What I'm going to show you includes only the contribution of the downstream region, not the shock transition layer itself. And it's important because, in my opinion, the greatest challenge is to actually explain the low energy part of the spectrum, not the high energy part. The high energy part you can produce by many models, but the low energy part is really tricky. And the other reason is that we haven't finished calculating the spectrum inside the shock. OK, so this is the idea. Of course, you need to specify the upstream conditions if you want to get some results. And the most important parameter, which has already been mentioned here several times, is this entropy, specific entropy, which is essentially the ratio of the photon density to the baryon density. So the question is, what is this number in the upstream flow? And we quantified by this parameter R naught. OK. And this is a whole different talk, but I think it can be actually larger than previously thought. Even just collimation itself will give you much dissipation. But also the injection process, for example, will give you, is quite extended. So this R naught can be between 10 to the 7 centimeters to 10 to the 8 centimeters for typical black holes masses. Okay, and then you can show that the nice thing about this is that the temperature just downstream of the shock in the observer frame is independent of the bulk Lorentz factor. It only depends on the Lorentz factor of the shock in the rest frame of the bulk flow, but not on the bulk Lorentz factor, up to some limits. And it's typically on the order of MC squared, give or take. And this is because, this number was computed assuming a adiabatic fireball. Namely, you started some R naught and expanded diabatically. And this is just a consequence of the essentially fact that the region where you dissipate energy is very compact. Okay, so this is a natural way to get the scale. Okay, now what's the idea in this calculation? As I said, I'm interested in the integrated spectrum. But each shocked shell has a different temperature. So the idea is to calculate the temperature of each shocked shell at the photosphere depending on the radius at which it's produced. Suppose, for example, that your shock was initially produced at R naught, and then it propagates all the way out. So now let's suppose that it's temporarily, at some given time, it has reached this radius Rs, and now a new shock shell material was produced because some new fresh material was crossing the shock. So now the shock continues to propagate, and the shock shell also propagates outwards, but slightly slower than the shock. And now I know what is the temperature of the shell here because I use the jump condition. If I know the shock velocity here, I can easily calculate the temperature Ts from the jump conditions. And then what I have to do, is to solve a radiative transfer problem of this shell up to the photosphere, and then I can get the photospheric temperature of this shell. So the jump condition is like an initial, is a boundary value for the transfer problem that I compute here. And there is a correspondence. For every radius Rs, where the shock was at a given time, there is a photospheric temperature, which you can get from this calculation. Okay, and then what I basically assume that for each shocked shell, the spectrum is Wayne in the short terminology with this local temperature, with this Tf. Of course, this T photospheric is different for different shells. So I know what is the local spectrum of each shell, and then I integrate over all these shells to get the time integrated spectrum. That's the game here. Now, what I described is a emission from a single shock so far. Okay. So now how it looks like, here are some examples. As I said, I'm only showing the contribution of the downstream region, not the shock itself. So there should be another component here which is missing. But basically, you see it's something which is thermal. By the way, you cannot get black body as people claim. It's a thermal spectrum, but it's not black body, no way. So it depends mainly on gamma, and for this choice so far, it's located here. But this really, there is an uncertainty in the entropy, so you have to keep in mind that there is some uncertainty in the location of each peak. But this is the scaling, it's kind of, you can analytically do, right? Yeah.
Just one comment about this is not black body. It's useless to try and extract radius.
Okay, I don't, okay.
Just a comment.
Okay. Okay.
It's useless to try and extract the radius by using black body formula from this spectrum.
Yeah, I think the guys that do that already revised their analysis, so it's okay. So basically, where was I? Yeah, here. Okay, so this is an example for relativistic shocks. And going back to this extreme example, you can actually, I don't like to play these games to fit data because, I have enough parameters, but it can quite naturally expand something like this, a single shock event. Okay. So, I said these are quite rare, but of course there is another underlying component. Okay. Okay. By the way, what you see here was computed for shocks with a constant velocity. I assume that the velocity of the shock is not changing along its course. Of course, you can think about situation where, reverse shock has crossed long ago and the shock is decelerating, for example. And so you can play these games. Here an example of a decelerating shock. And this dependence corresponds to a blast wave propagating in a wind. It's not terribly important, but we are now looking at all these possibilities. Here is the same for non-relativistic or mildly relativistic shocks. The main difference is that the peak is shifted. And by the way, there is a minimum velocity at which you can form a shock. If it's smaller than this value, the shock is subsonic. I mean, the flow is subsonic, and you cannot form a shock. So anyway, here you see the dependence of the slope on the optical depth where the shock is formed. And as you expect, the reason why this slope becomes essentially becomes softer is because you produce more photons at these optical depths. So essentially here you start seeing the photon production effect. Okay, so a single shock event can explain some of the rare bursts, but it definitely looks like nothing like a typical spectrum. On the other hand, you may ask this question, as I showed you earlier, at least in the case of internal shock, we do expect sometimes to see emission from multiple shocks, or we do expect spread in this parameter. So one calculation which you can do is to see what is the spectrum contributed by several shocks with different strengths. Okay, a range of strengths. So this is what I'm going to show you next. This is a work in progress, so some of the results are preliminary. But the main conclusion is I'll show you that if you spread the parameters, namely if you have several shocks with a spread in the velocities, or if the shocks are decelerating, the spread in the location where they formed, you quite naturally produce a low energy tail, which is a power law with index between 1 and 2 in the NIFNI. So here is an example. This is the spectrum produced by several shocks. So what we did here, we computed the contribution from a single shock, and we just integrated over all shocks. And you see that you get something like this. The slope is, in this particular example, is quite robust. But if you have a small number of shocks, you sometimes see some wiggles. I'll get back to it in a minute. But the peak is determined by the shocks that were produced at the lowest optical depths, typically. Here is a similar example, but let's say this is a contribution of 4 shocks. And you see, again, there is an average power law, but there is some wiggles here. If this were real data, people would just put a straight line here. Actually, I'm going to show that, to argue that there may be evidence for wiggles in the spectrum. Okay, so here, speaking about the wiggles, this has been shown, but I'm not going to make a big fuss about it. But if you look at this, you do see some things like that. Now, this may not be real, actually. I don't know. I mean, there are any observers. This may not be real. On the other hand, they are not unlike. Sorry?
Everything's impossible. It can be this because you are.
But there is, in some cases, evidence for things like that. So if these features are real, then it's a reasonable explanation. That's all I can say. Okay, here is another example, the one I showed you before. Again, as I said, the interpretation here was that this is one component and this is some non-thermal. Basically, my student just computed, tried to feed this. It turns out that you can feed the spectrum, and you see here the result, with something like several shocks, 4 or 5 shocks, which are not equally spaced. So you can actually get this entire thing from a photospheric emission by several shocks. Again, the high energy part is missing here. So, sorry?
Do you know what's the time integration? What's the time resolution on this spectrum?
No, it depends on, again, on on the width of the shock you're assuming.
No. But this observation, taken
this?
over what?
Oh, I think this is the entire event, if I'm not mistaken. No. This is the entire. So, basically, in general, what you expect from this is, even though it's photospheric emission, you are going to have things that look highly non-thermal. So the fact that you have a non-thermal extension, both at high energies and low energies, is not surprising. Photospheric emission doesn't mean black body or anything like that. Secondly, another point is that the photospheric emission is quite efficient, typically. It's more efficient, typically, than the collisionless phase. And again, I don't think 50% efficiency is some limit that I think is, yeah. But 10, 20, 30% is not a big problem. For example, I computed the efficiency of such an internal shocks, subphotospheric shock for gamma of 2. And I get something like 30%. So it's quite efficient. You expect, in case of multiple shock emission, you expect a range of properties. But again, this typical average slope, this is something quite robust. If you spread out the properties, you get this quite robust, and you can get some substructure. And as suggested here by Lorenzo, you expect to see a variability if you have good enough time resolution. And one last point before I finish is that we also expect, and this is not just because we need it, but we, on theoretical grounds, we do expect another contribution from the collisionless phase. And the point is the following. If you have a shock propagating below the photosphere and it still has enough energy when it reaches when it breaks out, it will become collisionless, okay, at some point. So after it breaks out, it becomes collisionless, and then if it accelerates particles in this phase, in principle it can accelerate particles, you do expect now to have, this is something similar to the GV flashes that Inrik and Andre worked on. You expect to have Compton scattering of the emission coming from behind, from the downstream region, which is still emitting. So there is like the shock is collisionless, this downstream region is still emitting. And the question is, what is the relative importance of this contribution? This is something we are actually computing now. It's a simple exercise. But I mean, the answer may be interesting. And I think in many events, especially in the efficient ones, you do expect this. It should be inherent in the spectrum that you see, this contribution from the collisionless phase. So, I mean, life may be more complicated. The question is, how it looks like and what is the relative energies in these two phases. And so I think with this, I can actually finish. And these are the conclusions. I already mentioned them during the talk, so if you want, you can read them or not. OK, thank you.